helpful you do the.
So, hello. In today's video, I would like to address the Legendre transformation. So this transformation is often used in physical chemistry, in particular in thermodynamics, to obtain quantities like enthalpy or Gibbs free energy from the inner energy via variable transformation. So that's the motivation why we had in this lecture series. And let's have a start in explaining what the Legendre transformation actually is. So first, let's say we have a convex function which we call f of x, and since it is convex, f double prime of x is greater than 0 for all x. And next, we define a linear function let's call it g of x, and this is g of x equals p times x. And for completeness, p and x are elements of the real numbers. So the next I would like to do is graphically illustrate what we have here. So let's draw a y-axis and an x-axis. And first draw the function g of x, which goes like this. And the function f of x, which may go like this if it is strictly convex for all x. And the next thing we have to do for covering the Legendre transformation, we define a new function f star. F star, which depends on p, and it is defined as the supremum of p times x minus f of x. For all x that are real numbers. So actually what this means is that for this function we are searching for the maximum difference between g of x and f of x, or an upper boundary. So let's write this down, what we are searching for. So we are searching for a maximum or an upper boundary, but I will not write it here because I assume now that there a maximum for this exists. For a maximum difference between g of x and f of x. And this means to get the maximum value for this here, we have to find a certain x naught for which this expression here is maximized. This means we have to find corresponding x naught. So, in the next step, we have to analytically find a maximum for this expression here, namely a maximum, and accordingly the x naught for which this expression here is maximized. So therefore let's differentiate this term in the brackets. So d over dx px minus f of x equals p minus f prime of x. And if we differentiate this again, second time, which is the second derivative of f star, or this fact that the term in between the brackets is p minus f prime x. This equals minus f double prime of x. And because we said f double prime of x is strictly greater than 0, this must be always lower than 0, and this here confirms that indeed what we will obtain after setting this here 0 is the maximum. So now I will erase the board, and maybe it's good if you're interested to note write down this definition here, or I will write it down here again to keep it throughout the next steps. It's defined as the supremum for real numbers. For x can be any real number, p times x minus fx. And now erase everything here because we need some space. And write again here this derivative. Prime of x. And if to find the maximum, we have to set this expression to 0. So p minus f prime of x naught equals 0. That means p equals f prime at x naught. This is already with this expression we already know where x naught has to be at the x-axis, because originally we have here already defined the slope. The slope is defined with the function g of x, and for a particular slope or a value of p, we can obtain x naught, because this here is p of x, and x naught is located at the position where the derivative of x equals p, and this means graphically here we have f of x, and a certain point the first derivative of f of x equals p, and x naught. And we can also rewrite this, be more precise. So we have f prime of p, f prime inverse of p equals x naught. So that's the analytical expression for x naught, which I have graphically drawn here. So now, after having found x naught, we can plug it in here, because we know at x naught this expression here within the brackets is maximized. So let's do this. So f prime for a given p, in our case it can be any real number, so f star is a function of p, and p belongs to the real numbers. It is p, and now we just have to copy x naught. Hopefully I'm not making any mistake here. So actually we had already now finished with evaluating or finding f star of p. Next step is just I would like to write it in a more, let's say, concise manner. Let's say here we have again p times x naught, the x for which the expression here becomes maximized, but x naught again is a function of p. Because for a given p, x naught varies. Minus function originally defined, which is convex for all real numbers, is also a function of x naught, which depends on p. So now this is already our first result. We know in principle now how to calculate the Legendre transform of a given convex function. In the next step, I would like to give a geometric interpretation of the Legendre transformation. So therefore now I will clean the whole board, or almost the whole board. So the original definitions, let's keep it. Let's keep them. So now let's draw again our coordinate system. And draw the function f of x. And also write again f prime, like we have found it before cleaning the board. It is p of x naught minus f of x naught. And p we have found is f prime at x naught times x naught minus f of x naught. And to make a geometric interpretation with this, we first have a look at the tangent to the function f of x at x naught. So let's do this. Tangent line, tangent at x naught. Let's call it h. So h of x equals f evaluated x at x naught plus f prime at x naught times x minus x naught. And h evaluated at 0 equals f evaluated at x naught minus f prime evaluated at x naught times x naught. And the next step, let's draw this function here. Let's say here, let's say here is the position of x naught. Then we have to draw a tangent. Oh, this is h of x. And this value here, h0, is the y-intercept of the tangent to hf at x naught. And by comparing this expression here for by comparing the expression for x prime and h evaluated at 0, we find that it is the negative value of h evaluated at 0 so the graphic interpretation of the Legendre transform is, so let's mark this, is that we have shifted the information given by x and f of x to a pair of slopes, and the slopes have corresponding negative y-intercept values. I hope this is clear. For clarity, I will also write here on the board what the geometric interpretation is. So f star of p describes the negative so hopefully this is clear. Let's repeat again what we have found. So we have started with the function f of x, which is convex for all x, and this function is, let's say, codes, so to say, information with the pair x and the corresponding f of x. And by applying the Legendre transformation, we have shifted the information contained here to the pair p and f star of p. And in the one-dimensional case, the geometric interpretation is that p is the value of the first derivative of this function, and the value for the first derivative being p has a corresponding x naught and also a corresponding negative y-intercept value here. In the next step of this video, I will give example with graphics of how to interpret this variable transformation again.